Okay, so our next speaker is Dolev Bluvstein, who is one of the major players in Misha Lukin's lab on neutral atom quantum computing. So Dolev's now at Caltech, and looking forward to your talk.
Thank you. Just a little bit. So I'm going to tell you today about our work developing neutral atom quantum processors and using them for quantum error correction. I am, at this point in my life, I think both a physicist and an engineer. I was debating whether to give the physicist description or the engineer description. This one was actually the one that's more on the engineer side. So we would like to build quantum computers that work. Last time I was here, I gave more of a physicist description. Okay, I guess maybe there's a mix of the two. So anyway, building quantum computers is really hard, and we have all these applications that we're really excited about. But it's fundamentally pretty hard to operate on quantum information and to store it robustly. If we have classical information, like a classical bit 0, and it gets, for example, measured by its environment, then it gets redundantly stored. But if we have a quantum bit in state psi, and then we take pictures of it, it probabilistically collapses and leads to an irreversible type of decoherence. And so we already see that classical and quantum information are quite different in the way that the information is stored and how it interacts with its environment. Another very subtle thing with quantum systems is that if you have, for example, a chain of spins interacting, and you're trying to use this as a computation, and they're all interacting with some interactions j, and you can read off the state of your system as a way to do computation, if j is just slightly off and goes to some state j plus epsilon, then you can go to a chaotically very different state. And this is not a robust way of doing computation. And I am not an expert on complexity theory, but it is at least my understanding that actually analog classical computers are strictly more powerful than quantum computers. And analog classical computers are so powerful because they can represent continuous real numbers. And that is a much more efficient way of representing information. But we don't use analog computers often. We use digital computers that are composed out of bits. And the reason for that is because they're correctable. And small voltage imperfections, for example, get rectified to going to either bit 0 or bit 1. And this seems at odds with what we have with quantum mechanics, where we have, for example, Bloch spheres that have continuous or analog angles that are intrinsically sensitive to imperfections. So something that we see is that if we want to build quantum computers, we really need a way to correct errors. And it seems quite fundamental due to this issue. Remarkably, it is possible to do quantum error correction. And my bit in the beginning about physics and engineering is because I think it's really just such a remarkable thing from a physical perspective that it's even physically possible to do this. And it actually works in a very different way than classical error correction, which just works by copying bits. The way quantum error correction works is you take a logical qubit degree of freedom that you're interested in, and then you hide it by delocalizing it across many individual physical qubits using entanglement. And by being delocalized, this logical qubit degree of freedom becomes hard to accidentally manipulate. And it becomes hard for the environment to now, for example, accidentally measure this logical qubit degree of freedom. And although we can't measure individual qubits without destroying the state, remarkably, we can measure products of qubits, or these so-called stabilizer checks, in order to detect errors while preserving the encoded information. And below a characteristic threshold in the system, this starts to allow doing exponential error suppression, where the logical error rate in the system can get, in principle, exponentially suppressed with increasing the code distance d, which is the linear dimension of the system, as long as the errors are below some characteristic threshold. And this characteristic threshold is at the scale of 1%. And this now starts to make it realistic to get to extremely small error rates. And this was really one of the key things that actually led to the development of quantum computing, because it started to become clear that this is actually something that you can realistically do. And I think it's truly remarkable that quantum error correction is even physically possible. And I think that's well captured by this famous argument between Peter Shor and Rolf Landauer at the beginning of the field, where Shor invented this factoring algorithm, and then Landauer was very publicly questioning him, saying, you're describing an analog computation. We know we can't correct analog computers. What here is even new? And the response, to paraphrase, is that although the computation is analog, the errors are digital. And it's really uniquely due to the wave-particle duality that it is even physically possible to do analog-style quantum computations with logical qubits that are stored in the entanglement between the physical qubits while removing errors from the system. And error correction is a very powerful tool. It allows us to build very low error rate systems that we want to go use for advanced computations, but it's also, I think, just remarkable from a physics perspective. That said, error correction is extremely challenging. So when we think about the estimates that we require to get to large-scale problems, we often have numbers like, for example, in what Craig just described in his talk, at the scale of millions of physical qubits to allow us to get to thousands of logical qubits with error rates at the scale of 10 to the minus 10 and below. And that is a lot of qubits, and it's so far in the field been greatly compounded by the challenge of doing efficient classical control. In our quantum computers, a lot of the quantum computers we've built so far work in this way where you make a small device in the lab, and you do it qubit by qubit, and then you try to scale it up by increasing the size of the system, adding more connections and more wires to each qubit. And that's quite different than the way we do control in, for example, our classical computers, where we've gotten very good at doing things like taking 1,000 wires to control billions of bits in the system. One very key challenge is that this so-called wire problem poses a significant challenge to getting to large-scale control over millions of qubits. Another central challenge is that once this logical qubit is delocalized, it becomes really hard to operate on. It becomes protected from its environment, but also becomes protected from other qubits. So as of a few years ago, this large overheads and the complexity of operating on logical qubits had focused studies in the field to the scale of 1 or 2 logical qubits and gates. What I will tell you about today are techniques that we've developed in order to do advanced computation and error-corrected computation with neutral atoms trapped inside of optical tweezers. And in these so-called reconfigurable atom array system, what this looks like is we have tightly focused beams of light, or optical tweezers, and we have neutral atoms that get trapped inside of each of these tightly focused beams of light. And we store coherence inside of the atom, inside of something that's effectively a nuclear spin inside of this atom, this hyperfine qubit, and has coherence times on the scale of several seconds. And when we want to entangle 2 atoms, what we do is we zap them with a very precisely tuned laser frequency. This excites them to a high-lying orbital state, which we call a so-called Rydberg state. And this generates entanglement. Excuse me. The coherence is so long that we can, in fact, move the atoms around in the middle of the computation. And what this allows us to do is dynamically reshuffle our atoms, pulse a global laser, excuse me, and in this way program complex circuits. Someone else who is a key pioneer of this technology is Harry Levine, who is here at Berkeley for people who are at Berkeley. But this gives us 2 really unique opportunities for quantum error correction. One is non-local connectivity, which it turns out for error correction is extremely powerful. And 2 is the ability to do parallel and efficient classical control. So this is one of the first quantum circuits we ever ran. Here we made this so-called toric code on a torus with periodic boundary conditions. And this movie shows how we program quantum circuits. So we have 16 atoms that are data qubits here, and they're fixed in tweezers. And then we're using ancilla atoms that are in dynamically moving tweezers that are moving across the system in order to measure a stabilizer check. And we move these atoms into pairs, pulse a global laser, and this causes this red oval of entanglement. Move the atoms here all the way across the system to make periodic boundary conditions. And this is how we do here simple quantum circuits, just by moving atoms around, doing global laser pulses. While we were doing these first experiments, we started to understand that there was a really unique opportunity here for doing highly parallel processing on logical qubits. And in particular, if we want to now do quantum computation not between individual physical qubits, but between individual logical qubits, the problem becomes quite different and actually very naturally multiplexes with optics. For example, if I want to do a logical single qubit gate, what it turns out that I don't have to do is a unique operation to each individual physical qubit of the block. If I want to do a transversal, for example, Clifford gate on my surface code, I can take one big beam, and it's like one big Hadamard beam, and I illuminate this one big qubit with this one big beam. And this simple parallel step, I can do this single logical qubit operation. And crucially, we can also do this for 2 qubit gates, where we pick up the 2 blocks, interlace them with each other, do one global pulse of our entangling laser, and in this single parallel step, we can entangle pairwise all of the twins of the 2 blocks, and in this way realize efficient entangling operations between our logical qubits. And this one in particular is something that I really want to emphasize because it's one of the key things that's enabled us to do error-corrected computations with simple systems. Is this transversal C0 I think is quite special and quite fundamental. And what we discussed earlier is that the way that we do error correction is we take this logical qubit degree of freedom and then we delocalize it across many individual physical qubits. And that makes it hard to accidentally manipulate, but it also makes it hard to intentionally manipulate. And for example, if you have two delocalized wave functions on a chip and you're trying to interact them via some boundary, it's something that you can do, but it's quite hard. You have to do a lot of very precise operations in order to get these two wave functions to interact with each other. But if you can just take these two blocks, put them right on top of each other, and in a single parallel step entangle these two wave functions while they're still delocalized and hidden, then in this transversal C0 way, you get a lot of benefits in that we've flushed this out over the past few years. So one is that this approach is inherently fault-tolerant. And what we now understand quite well is that this allows you to reduce the amount of error correction you have to do. You can go away from the so-called D rounds of error correction to do only roughly 1 round of stabilizer measurement needed between logic operations. Fault tolerance means that errors cannot spread within the code block in this context here. In the context of algorithms, it gives you long range and direct connections between logical qubits. We don't have to think necessarily about hallways. Maybe there's other kind of complications. But you can just think about connecting two logical qubits directly. And lastly, from an experimental perspective, the thing that cannot possibly be emphasized enough is that of efficient classical control. All of the physical qubits in this logical block receive the exact same instruction and just effectively act like one big atom. So using these principles, in 2023, we developed this first generation logical processor where we have logical blocks stored in storage zones where we have long coherence times. When we want to entangle two qubits, we pick them up, move them into the entangling zone, interlace them, and entangle them with a single pulse of the laser beam. And then when we want to measure atoms, we can move them to a separate readout zone where we can measure separate atoms without disturbing the atoms that are still active in the computation. And we studied various things with this approach. So one, and I'll just briefly overview them. So one is we studied the role of code distance in improving entangling operations. And here we prepared surface codes by doing a single round of stabilizer measurements with ancilla qubits, moved the ancillas away, and then did the entangling operations between these codes. And then studied how this works going from distance 3 to distance 5 to distance 7. And what we found here is that we get very, very slow improvement in the gate performance as we increase the code size. We want to get to 10 to the minus 10, so this is not 10 to the minus 10. But we start to see that things can improve as we increase the size of the code. We also learned a lot of practical lessons about the importance of how we do this so-called decoding, which is the inference process of when I look at the stabilizers, how do I infer what errors happen in the system. And in particular, we developed these so-called correlated decoding techniques, very related to so-called space-time decoding in the literature. And broadly, the observation here is that when we're doing algorithms between logical qubits, it really makes a lot of sense not to consider logical qubits independently, but to consider the algorithm as a whole. And what you even define as your logical qubit starts to change once you start doing quantum circuits. And we learned a lot of theoretical insights here in terms of ways to, for example, reduce the overhead of computation from D rounds to 1 round in terms of how many error correction rounds one needs to do. That was one key lesson. Another key lesson is that in building logical processors in the lab, there's a lot of funny subtleties that come into it. There's many, many different complex error correcting codes people have developed at this point, from LDPC codes, 3D codes, 4D codes, surface codes. And algorithms are also very subtle. So it's quite subtle how you think about designing error correcting codes, algorithms, and hardware all together. And it's a complex art form that when you play this complex art form, it allows you to come up with new creative tricks. And one of the big things that is fundamental to the fact that you want to do digital operations with these error correcting systems is that you only have a discrete gate set available to you, like a Hadamard, S, or C0. 2D codes in particular only have Clifford gates, and you need non-Clifford gates to do things that are interesting, like classically complex simulations. And it starts to just become a completely different world than what we're used to after several decades of playing with qubits in the lab. These are completely different types of qubits, where Actually, one of the easiest things you can do is a transversal C0. And entanglement is very easy. But continuous rotations are actually one of the hardest things you can do. It's the opposite of what we always used to tell our theorist friends several years ago. So it's a completely new type of system. Here, what we studied was doing quantum simulation or quantum scrambling by using discrete gates, where we used small 3D codes. And with these small 3D codes, we did several hundred logical operations, including up to 48 logical CCZs that were encoded efficiently within this 3D block. And it's not, doing an arbitrary quantum simulation here. It's just doing a particular type of quantum scrambling simulation that we could really efficiently implement with these codes. And here, for this particular measurements, we used error detection, which means post-selection. But with this post-selection, we were still able to do quite a bit better at sampling tasks with our error correcting, our logical qubit system, compared to what we were able to do with physical qubits for the same circuit. Okay. So we learned a lot of lessons from doing this. And here the goal was to start doing error-corrected algorithms in the lab and do experiments poking in many different corners and see what we learn. And we learned a lot of things. The first finding that cannot possibly be emphasized enough is that the main way that we're able to do these experiments, and this is just a few students in a basement of a lab, is by parallel control over logical qubit blocks. This is the first logical circuit we ever did, where we had an array of steam codes that we started entangling together into a GHE state. And this is the drawing that we draw for ourselves in the lab on the back of a mini circuits data sheet. And the reason you can do this is we're not programming a very complex 70 physical qubit circuit. We're just doing large parallel operations on our steam codes. And this makes it significantly easier. So this, I think, is by far the key takeaway from our experiments. There's also other important takeaways we learned. We learned about the importance of considering algorithms as a whole. And this has led to a d-round saving in the error correction overhead. We learned about the importance of doing fault-tolerant compiling, designing algorithms and error-correcting codes in this special way together, how errors get digitized when you do error correction. And broadly, I think something we've been experiencing in our efforts is a transition in the theory that we do, focusing the algorithms we study to error-corrected implementations, and focusing the error correction we study to the implementation of algorithms. So this was our first set of studies, and we learned a lot from doing that. But after having gotten more grounding in what does it look like to do error-corrected algorithms, we wanted to really much more systematically understand what do you need and what do you not need in order to build a universal fault-tolerant quantum computer. And so here, in order to do that, we implemented all of the elements that we believe one would need for universal fault-tolerant computation. We studied very deeply how do these underlying mechanisms work, what things are required, what things are not required, and extracted some key lessons that allowed us to improve our error correction architecture. This is all described in this paper here. This paper is extremely dense, so I cannot possibly overview all of it, but I'll overview some key aspects. So one is that we did a benchmark in our system, and this is really just a kind of classic fidelity benchmark, heavily inspired by the Google team, where we took a surface code and here did 4 rounds of error correction and studied how well does the error correction improve when we go from distance 3 to distance 5, and we use techniques such as loss detection and machine learning decoding to improve our performance. That is one key kind of fidelity benchmark. Another key aspect was developing an architecture that allows us to do fault-tolerant processing in a way that's also well amenable to doing universal operations, where we have multiple zones, and then we cycle atoms in these multiple zones in order to do computation, but also extract errors from the system in a fridge-like fashion. So one of the key technical tools enabling these new experiments is a different type of way of doing readout that I want to overview in part because it's so much fun. In conventional readout schemes, with atoms, one of the big challenges is that imaging mixes your qubit states together that are stored within the atom. And so the typical trick that we play is that we convert one of the spin states to loss, and then we image whether the atom is there or not. And it's a very robust way of imaging, but you lose half your atoms every time you do the imaging. There's a lot of benefits of doing lossless state-resolved readouts. So one is that you can reuse your atoms, and you can do many more rounds of error correction using the same number of atoms. And 2 is that it directly detects loss and improves your error correction performance, as is greatly inspired by, for example, Jeff and Shruti. And here, in order to do this, we implemented a spin-to-position conversion as opposed to a spin-to-loss conversion. where we take an optical lattice and shine this optical lattice on these atoms, and then move the atoms in their tweezers to separate them. And one of the atoms gets pinned by the lattice, and the other one doesn't, and just moves freely through the lattice. And then we image the atom's position. And then here we measure the Rabi oscillations. So this is what Rabi oscillations look like measured with a spin-to-position conversion. We tried roughly 5 new techniques, I would say, for non-destructive readout, and we have this amazing track record that the technique that ends up working the best is also typically the one that looks the coolest. So this is how we now measure our qubit states. And we use this also to detect loss. It's not exactly an erasure detection. It's more of a delayed erasure, because you only get information about the loss later. And with this 4 rounds of error correction on the surface code, we see that we can be roughly a factor of 2 times below threshold by here using this machine learning and loss techniques. We get quite a bit better than if we were to just do conventional most likely error decoding without this loss information. One key important caveat is that threshold is very circuit dependent. If we add transversal gates and correlated decoding, this gives a roughly, in theory, up to roughly a 10% reduction. And if we went to infinite depth, then in theory it could reduce the threshold by another factor of roughly 15%. But it's at the scale of roughly a factor of 2 below the threshold. Here we have an error budget. We also did detailed simulations comparing our experiment to simple error models. Broadly, we find that the error distribution agrees very well with simple simulations. We've yet to observe large-scale correlated errors, which I can describe for people who are interested. We also find that leakage is strongly dominated by loss in our system, actually more than we're expecting due to something that seems like a native erasure conversion that the atoms experience. And we're currently a factor of roughly 2 times below the threshold, but we'd like to get to roughly a factor of 5 below the threshold. But I think it's quite promising. I think the approach that we can take here looking at this error budget is to fix single qubit errors. So a lot of these single qubit errors I would describe as essentially bugs. They're things that we've gotten to work much better before, and I think this is pretty realistic to reduce this by a factor of roughly 3. And then we can improve our 2 qubit error by a factor of roughly 2 by increasing the laser power by a factor of roughly 4. And I think these are realistic paths forward in order to get to 5 times below the threshold. So I would say the main summary of these experiments in this benchmarking is that with effort, after calibrating the system carefully, et cetera, and using this loss information, using machine learning, we're able to get the performance we expect. And we have yet to see any kind of unexpected surprises in terms of things that did not work in the way that we wanted them to for this below threshold experiment. That's one important technical aspect. Another important technical aspect is how do you set up the architecture in order to be able to do deep circuit processing? So one of the things I had to skip over is that once you start doing all these transversal gates, it starts to become very different how to think about what is the key unit of error correction in the architecture. It's actually not so much anymore one cycle of error correction or one cycle of stabilizer measurement. The stabilizer measurement removes entropy, but the thing that's actually quite fundamental is teleportation. It's a really key unit in the processor. Teleportation, natively removes errors, and it also can natively do loss detection. And it also enables the realization of magic, which is actually really the only thing that is powerful inside of the quantum computer, or the key thing that's powerful inside of the quantum computer. And so we set up this architecture for deep circuit processing in a way that allows us to just maximize the number of teleportations we can do. And we studied this with multiple different types of codes. And here in particular, I'm showing Stein codes, where we have 27 time layers and 16 codes per layer. And we entangle atoms within a space layer, but we also entangle them between different time layers. And here did up to several hundred, or in some cases up to 1,000 logical teleportations. And this movie shows what this looks like. So we have, we pick up atoms from this readout zone, and then we start entangling them into Stein codes in this entangling zone. Then we start taking the Stein codes and entangling them together into cluster states in the space direction. We take a previous block and entangle it in the time direction. We use the lattice to split the atoms here in half, which is so satisfying to watch. And then then the atoms are flickering, and it depends on which of the 2 directions, which of the spin states they were in, whether they went up or down. And then in a second, we're going to put the atoms back. And then we also can refill atoms from our reservoir, and we reuse this. And it's like a fridge. When you do the computation, it's imperfect. It generates entropy. That's a very fundamental thing. And then you have to remove entropy. And that's what this fridge-like process does. And I think teleportation is really a very key way of thinking about the whole thing. And this is what our poor atoms are going through in order to make cluster states. which is just a simple prototype here for doing deep circuit computations based off teleportation. Here we're making these 2D cluster states on the logical level by processing through these atoms in this deep circuit architecture. And we see that the cluster state stabilizers are good and are near the expected values until we start to run out of atoms here, and then our depletion starts to take off because we're not continuously reloading the atoms in this particular experiments. So this is roughly half of the paper that we have here. I can't talk about the rest of it, but I want some people in the world to know what's in this paper. So just to briefly overview. So here, these are more technical aspects. But we also have a lot of really fun physics in this paper that I think is really interesting. And at least for me, it's really helpful for thinking about what do you and don't you need to do for universal fault-tolerant processing. So one thing, for example, is we really studied the core physical mechanisms of how entropy gets removed when you do the error correction, both through the Zeno effect as well as tracking and removing entropy. We studied how this entropy removal gets interspersed with fault-tolerant logic and how that interfaces with the so-called correlated decoding technique and being able to reduce the number of error correction rounds one needs to do. As well as efficient mechanisms for how to do arbitrary unitary operations on logical qubits, even in ways that are fully transversal. Broadly, I think we now just have a much cleaner understanding of what things you do and don't need to do universal fault-tolerant processing, and have a simplified framework in mind. And here we studied in this paper also in the methods, generalized techniques for syndrome extraction, erasure information and machine learning, lattice surgery, and transversal operations, unitary synthesis and code switching, as well as high-rate encodings, where we also did for these deep circuit experiments. We used 1664 codes. It's a very broad range of things. But the thing that was so useful about that is we were able to touch different corners and get a kind of holistic understanding of what things are and are not helpful in this fault-tolerant processor. And just to flash, so also for people that it's helpful, we also have a lot of extra data in the paper. So these in ED Figure 1. Is this schematic of exactly what our processor looks like. We also have raw data for the surface code, as well as a bunch of other ancillary files, such as the error model we have and the simulation procedure that reproduces this 2 times below threshold result, as well as the raw experimental commands that this is all of the circuits that we do, we still type them all out completely by hand manually, where we tell each atom where to move on each individual moment in time, which is something that we should improve. So those are some of the error correction aspects, but also for atomic physics and for improving the error correction further. These tools are really fun. So we can, for example, now by reusing the atoms, do much faster cycle rates. And I think for someone who's an expert on transmons, this is maybe not going to be so impressive. But for atomic physicists, this is really fun. So this is real time how fast we can do Rabi oscillations now. So this is real time data coming in, doing data traces where we're rapidly reusing the atoms and can get to much higher cycle rates. And leveraging this significant cycle rate improvement also with the parallelism that you get across hundreds of atoms, we get to data rates that can be as fast as a transmon for calibration. Also in work that was spearheaded by this so-called Atom Array 2 team that worked very, very hard on these results in the Harvard lab. We explored how to do continuous operations for much, much longer times on the scale of up to hours, where here, building large arrays piece by piece and continuously maintaining an array while also being able to preserve coherence. And here with, again, this multiple different zones, loading atoms, loading them into preparation and storage zones, we see that we're able to maintain largely defect-free configurations of up to several thousand atoms, up to 3,000 atoms for the scale of several hours. And here so far, these are not combined, but you can see kind of here we have our understanding of how to do this fault-tolerant processing architecture. And here, the reloading rates that are achieved are significantly higher than what's required to replenish the atoms that are lost from the reservoir when we do these experiments. So it's a pretty exciting frontier for both neutral atoms and for quantum error correction. The developments across the field for neutral atoms, I think, are extremely exciting, both in terms of scaling to much larger systems, connecting different modules, exploring different species, exploring different types of error correcting codes and optical tools. I think it's going to be a very exciting frontier on the neutral atom front. But also on the error correction front, it's quite remarkable how many different systems start to cross characteristic thresholds all at the same time, both in terms of system sizes and fidelity. This Google paper, for example, from late 2024 is a real highlight, seeing this very clear exponential suppression for the first time. Also really impressive work from Quantinuum, Amazon and Caltech team, and also just a lot of amazing theoretical developments as well as from Yale. And I think the thing I love about this is like all these different developments. I mean, if you look at the archive identifiers, it's really amazing how rapidly these things are happening. It's like end of 2024, beginning of 2025. And I think it's starting to become extremely clear that error correction works. And it's at a real inflection point. It's also a really remarkable exchange of ideas between systems that are so disparate, which I think is quite amazing. I think it should be in a pretty exciting next few years. Thank you. That's the end of my talk. I would like to acknowledge the amazing colleagues I was able to work with during my PhD, in particular this atom array team. So I am gone now, which is sad, but they're still a very strong team. And in particular, I really want to acknowledge Sasha, who worked extremely hard on these experiments I showed today, and is also extremely bright. And she's going into her third year now, so you should continue to monitor what she and the rest of the team are doing. And finally, I am starting a lab at Caltech, and you should come visit us, because we would love to collaborate. And we're also looking for students and postdocs to add to our team. So thank you.
Maybe time for a quick question.
Optically, are you somehow limited by how many atoms or logical qubits you can address during one of these algorithms?
Like in terms of how many we can address in parallel?
Yeah, like for this parallelized algorithm.
Yeah, so it is. So the big limit right now is laser power. So for example, we have an entangling zone. So one of the things that's amazing is that you can do almost everything in parallel, both on the making the error correcting qubit as well as using the error correcting qubits for algorithms, depending on the algorithm. And you just want to have, but still we need, estimates of like millions of qubits. We currently have, like maybe generously call it 1,000, right? So then you need to make these things much, much bigger. And you need much more efficient ways of using the laser power. And that's something that we're going to explore at Caltech are, ways, for example, to do much more efficient, try to reduce the amount of laser power we need by, significant factors.
Great, thanks, Dolev. So let's take a break until 11. Thank you.